Okay, so the first talk I'm going to give just now is about SpaceFibre and is the scheduled talk. But before I do that, we have a number of SpaceWire users guides. So I think we've got 6 here, and at the moment we've got another 6 we can bring tomorrow. So if anybody wants one of these booklets about SpaceWire, then just ask my colleague down the front here, and he'll be happy to give you one. Okay, so this work on SpaceFibre has been done mainly by the University of Dundee, by myself and some colleagues both at the university and at Star Dundee. So I'm going to talk about the need for SpaceFibre first of all. I'll talk about the SpaceFibre standard and the work we're doing on standardization. The quality of service that we've integrated in SpaceFibre, SpaceFibre chips that are being developed, test equipment, the validation that's being done with this protocol, and then talk about current and planned work. So I've already presented this slide earlier on about SpaceWire. SpaceWire is being used in over 100 spacecraft now, but there are some applications that SpaceWire doesn't fulfill. In particular, very high data rate applications. And that's what we're trying to cover with SpaceFibre. So those high data rate instruments are things like synthetic aperture radar and high resolution multispectral imaging systems. So that's the primary driver for developing SpaceFibre technology. But we also have a need for integrated control and data handling networks on board a spacecraft, where we can combine the instrument data handling that SpaceWire does, for example, with equipment control, housekeeping, gathering, time distribution, all over the same network, saving mass and power. We have a need for determinism for AOCS type applications and other control applications. There's a need for long-distance communications, so we can support launcher applications. We want to have galvanic isolation and improved FDIR capabilities, so we can improve the overall reliability and robustness of onboard networks. And there's a need for integrated quality of service. So this is normally provided by software, but we want to simplify the software and simplify the system design by providing this quality of service within the network, the onboard network itself. And there's a need for backwards compatibility with existing data handling technology, so in particular SpaceWire. So we want to be able to readily interconnect existing SpaceWire equipment with this new higher speed network technology. Okay, so the key features of SpaceFibre are, first of all, high performance. So with current space-qualified technology, we can achieve 2.5 gigabits per second. And we have plans to take this up to something like 6.5. When we apply multi-laning, we can go at, say, 20 gigabits per second. And within Europe, this is actually the highest data rate we can foresee for future SAR missions. That's at the moment, I guess. SpaceFibre provides galvanic isolation. It can run over both electrical and fiber optic cables, so it's not just limited to fiber optics, but over shorter distances it can run over electrical cables as well. It provides very low latency broadcast codes for signaling across the network. It has integrated quality of service, so we provide bandwidth reservation, priority, and scheduling integrated within in the hardware. We have integrated FDIR support, so the idea here is to provide that support as fault detection and recovery as close to where the fault occurs as possible. It has low implementation cost, and it's compatible with SpaceWire at the packet level. Okay, so the key thing about SpaceFibre is it's designed specifically for spaceflight applications. Okay, so to look at the SpaceFibre standard, this gives an overview of the protocol stack from the network layer down to the physical layer. So we just run through those levels of the protocol stack. First of all, starting off at the interfaces at the top and bottom. So if we think about SpaceWire, which people may be familiar with, then this shows a typical SpaceWire codec. So you have packet interface, timecode interface, management interface, and the serial interface. The packet interface is basically you put your packets in there and it will send them, and that's where you receive your SpaceWire packets. Timecodes, you can put in timecodes that you want to broadcast over the network or receive timecodes from there. And management is for things like setting the link speed, starting the link, and so on. If we look at a SpaceFibre codec, then it's actually very similar, except instead of the packet interface, we have a number of virtual channel interfaces. Each of these is like a pair of the SpaceWire FIFOs, so it can send and receive SpaceFibre packets. But because we've got several of these interfaces, it means we can send and receive several SpaceWire packets at the same time over a SpaceFibre network. We then have a broadcast interface, which is very similar to the timecode interface, except we've extended its capabilities, so we can broadcast short messages containing up to 8 bytes of information. We can do direct time distribution, so we can send time right across the network just in a single broadcast message. We can do synchronization of units, we can do event signaling, and we can also do error reporting by broadcasting error messages over the network. And then we have the management interface. Okay, so that gives you an idea of the interfaces into the IP core. So looking at the different layers, first of all, we've got the network layer. This is responsible for packaging information to be sent over the link and for transferring those packets over the network. The SpaceFibre packet is the same as SpaceWire. It has a destination address, cargo, which is the data you want to send, and an end-of-packet marker. The destination address can be either a path or a logical address. The network layer also handles broadcast messages. So as I've said, these are short messages which are basically broadcast right across the entire network. The management layer is responsible for configuring, controlling, and monitoring the status of the SpaceFibre network. The quality layer is effectively an additional layer that we've added in to provide quality of service and the FDIR capabilities, so fault detection, isolation, and recovery capabilities. It handles the virtual channels and provides the quality of service and flow control. It frames information into small frames so, for sending over the link so that we can interleave those frames and send information from multiple SpaceWire packets over a single SpaceFibre link. It also scrambles the SpaceFibre packet data if required so that to reduce EMC emissions from SpaceFibre. The retry mechanism recovers from transient errors, and in the trials we've done, we can basically recover from, you can be sending information over the link, and even if you've got a bit error rate of something like 10 to the minus 6, you will still get the data going through with no errors being seen, because we recover from those errors, and the only effect is as a slight degradation in the overall link performance by around about 5%. Okay, the multi-lane layer runs several SpaceFibre lanes in parallel to provide higher throughput, but it also, and uniquely, provides redundancy with graceful degradation. So if one lane fails, we can automatically switch to send the information over another lane, and it will do this either in a hot or cold redundancy sort of configuration. The lane layer provides initialization of a single lane and error detection for that lane, and it is responsible for encoding the information to be sent over the link. We use 8B, 10B encoding, which is DC balanced and supports galvanic isolation. The physical layer serializes the SpaceFibre symbols. It does the clock data recovery We also have, as well as a high-speed SpaceFibre, we can also run SpaceFibre at lower speed using an oversampled clock data recovery mechanism. So you can use this at multiple gigabit per second speeds with effectively very high performance clock data recovery, or you can use simpler techniques at lower speeds. And as I said, it runs over fibre or electrical medium. Okay, so that's given you an overview of the protocols. One of the things I wanted to concentrate on is the quality of service. So this, we have this integrated quality of service scheme which provides priority, bandwidth reservation and scheduling all at the same time. So priority is fairly obvious. The virtual channel, or VC, with the highest priority is the one that gets to send its information next. With bandwidth reservation, if we've got multiple virtual channels, we actually can allocate bandwidth to each of those virtual channels. And a virtual channel with some allocated bandwidth, which hasn't actually been using the link recently, so it's got low link utilization, will be the one that gets chosen to send its piece of information next. Scheduling, we actually chop time up into a series of time slots, which are synchronized, for example, by broadcast messages or local time. And the virtual channels are allocated to specific time slots. In an allocated time slot, a particular virtual channel or group of virtual channels are then allowed to send information. Okay, so we'll have a look at this in a bit more detail. So up here we see we've got 3 virtual channels, virtual channel 1, 2 and 3, going into a medium access controller, or MAC. That is selecting who goes next. That the information will be sent across the link, and at the other end we've got a demultiplexer. So the information for virtual channel 1 being sent at this end gets placed in virtual channel 1 buffer at the far end. So a virtual channel can send when a source virtual channel buffer has got some data to send. Okay, it's no point in sending something if you've got nothing to send. And also, the destination buffer has to have room for that, that piece of information to be sent. So if you've got something to send and there's room at the far end, you're allowed to send. Okay, and then of those virtual channels that have got something to send and there's room at the far end in their buffer, the one with the highest precedence is allowed to send next. I'll talk about precedence a bit more later on. Okay, so you can, at the moment you can think about it as priority. So the one with highest priority is the one that's allowed to go next. Okay, so here's an example. So virtual channel 1's got something to send and there's space in the buffer at the far end, so it can send the next frame of information. And then it still has some more to send and still has space in its buffer, so it's allowed to send the next frame. But then maybe virtual channel 2 now has something to send, and there's space at the far end, and it might be higher priority, so it can send the next frame of information. And then maybe virtual channel 3, which might even be higher priority, sends the next frame. Now virtual channels 2 and 3 haven't got any more information to send, or there's no room at the far end in their buffers, so virtual channel 1 can send the next frame of data. So we're multiplexing information across the link according to the priority, or more specifically, the precedence of each virtual channel. So the key thing here is a SpaceWire packet flowing through, or SpaceFibre packet flowing through one virtual channel doesn't block another packet flowing through another virtual channel. Okay, they're all completely independent of one another. Okay, so what I want to do now is talk about the quality of service and the bandwidth reservation mechanism. We worked very hard on this to get a very simple mechanism which would allow us to integrate bandwidth reservation, priority, and scheduling. And this is what we came up with. And it also has a whole load of other benefits, which I'll talk about as well. So what we have is a bandwidth credit counter. And this is simply a counter that, as it's like being paid. Okay, so you know, we go to work and we slowly accumulate funds, and that increases, and then every so often we go to the shops and we spend some of it, so it goes down. So here a a channel is slowly accumulating credit all the time, and every time it sends a frame, it basically spends some of that credit, which is what we see here. Okay, and then we can have multiple virtual channels doing the same thing. So here we've got 3 virtual channels. They're all accumulating credit at the same rate, and then every time they send a frame of information, they've spent some of their credit, and the credit counter drops down. You can see here, this one has actually dropped down twice as much as the other ones when it sends information. And this is because it's actually got a lower bandwidth allocated to it. So because it's got lower bandwidth, when it sends some information, it drops down further. Okay, and here we see that we've got 2 virtual channels. Both want to send at the same time, and it's the blue one that goes first because it's got higher precedence, and then after that the green one can go next. Okay, so I guess actually here you can see with the blue line, eventually it reaches the dotted line at the top and it saturates. So the counter will saturate when it reaches a maximum value. And the green line actually hits the saturation point at the lower end as well. Okay, so this is like the limits of our counter that we're using for counting this bandwidth reservation precedence. So to incorporate priority in this in a consistent way, what we've done is we've added a few extra bits at the top of that counter. Okay, so that gives us some extra range to our counter. But the individual bandwidth reservation counters, they can only clock up to a certain amount, and then these top bits are set according to priority. So that gives us, in this case, I've shown 3 priority levels. So you can imagine 4 priority levels using, say, 2 bits at the top of the counter. And then we've integrated priority with the bandwidth reservation. Okay, so we have a mechanism whereby if one of these bandwidth reservation counters reaches its lower limit, it then effectively is no longer allowed to compete. So when you've used up all your credit, you can't actually stop a lower priority virtual channel from sending information, okay, because you've used up all your credit anyway. So we can use this bandwidth allocation to make sure that channels with priority, they get to send whenever they want to, but we can also use it as a protection mechanism. So if somebody with high priority starts sending much more than they should, and they start using up more than their allocated bandwidth, then we can actually stop them from interfering with the rest of the system. We can also detect that somebody's hit or staying at this lower limit as well, and we can report that as an error. This is actually babbling idiot protection. So if somebody hits this lower level, they've actually used much more than their credit, so we can signal this as a babbling idiot detection. And finally, where we've gone up here with the flat peak, this is somebody who hasn't actually used up their bandwidth. So they're actually underutilizing the link. So in this case, we might want to report that, but it's not actually that critical. It's not like a babbling idiot. So we can do this by periodically just polling to see if somebody's stayed at this limit for a period of time. So maybe every millisecond or so, we might just check to see if somebody's stayed at there for a few milliseconds. Okay, so that's bandwidth reservation and priority integrated in a very simple mechanism which we can easily implement in hardware. And it's given us babbling idiot protection and some other fault detection mechanisms as well. We also provide the scheduling mechanism. So as I said, we chop time up into time slots, and in a particular time slot, a particular virtual channel can be set to send. Okay, so in time slot 1, we've allocated virtual channel 1 to send its information. So this is fully deterministic now. Nobody else is allowed to send. Virtual channel 2, we've got 2 time slots where we're allowed to send. In virtual channel 3, there's actually 2 virtual channels that are allowed to send. So these 2 virtual channels will now compete according to their precedence, so their priority and their bandwidth reservation. and whoever wins out will actually be the one that actually sends the next frame of information. Okay, so if you don't want to use the scheduling, then you just fill out your complete scheduling table like this, and it means that everybody will compete according to their priority and their bandwidth reservation. If you want to do something like have mixed deterministic, fully deterministic, and also some priority and bandwidth reservation, then you can actually do this sort of thing. So we've allocated some of the time slots for virtual channels 1, 2, 3, and 4, where they just compete on priority and bandwidth reservation. And other time slots we've allocated to virtual channels 5, 6, 7, and 8, and they've got fully deterministic access to the networking or the SpaceFibre link in that period of time. Okay, so that's the quality of service. So we've got this integrated quality of service mechanism, which is integrated in hardware. It's very simple, and it provides these 3 different communication mechanisms, quality of service mechanisms. We've also, in this layer, we've added in the FDIR capabilities. So first of all, there's fault detection. We use parity or disparity, as it's called in 8B, 10B encoding for detecting some errors. We can detect the invalid 8B and 10B codes. So 8B, 10B gives you, the 10 bits gives you 1,024 possibilities. Of those, we're only using 256 data values plus another 12 codes. All the other codes are invalid. So if you find one of those on your link, then you can detect that as being invalid. We've also designed the control codes that we're using in our frames and in our critical codes to have the maximum having distance. So it's not possible by a single bit error to convert, say, a data character into one of our critical control codes. Okay, so, and that's, again, that's something that's unique about SpaceFibre. We're also on our critical control codes, things like flow control tokens and so on, we've added in a small CRC to protect against any error. So and then we've got this over and underutilization of expected bandwidth detection. Isolation, well, at the physical level, we provide galvanic isolation. So a DC voltage will not propagate through the system and damage something at the far end of the link. We use data framing for time containment, so we're chopping information up into frames and containing errors within those frames. So each frame has a CRC, and we check for errors in that frame, so we've contained the error within that frame. And we also have containment within the virtual channels, basically containing the virtual channels within their allocated bandwidth. And finally, we've got fault recovery. So we've taken the approach that we want to recover the fault as close to where the actual fault occurs as possible. So we've introduced the link level retry. So that means when we send a frame of information across the link, we wait for an acknowledgement to come back before we basically release that from the transmit buffer. So this retry mechanism is very effective. We've actually designed a technique whereby we don't actually use timeouts for this. Okay, so the typical idea is you'll send your frame and you wait for the acknowledgement. If you don't receive the acknowledgement within a certain time, then you time out and then resend that frame again. We don't actually use timeouts. We've got another mechanism that's actually used to do this. So we're using acknowledgements, negative acknowledgements, and what we call polarity of the acknowledgements to basically remove the need for a timeout mechanism. So this means if you extend the length of the wire, then we automatically adopt to that. You don't have to tweak your timeout timers to cope with that sort of thing. The link level retry will, if there's an error on the link, it will retry and detect that, and recover from the link and resend the information within 5 microseconds. Okay, so this is one of the reasons why it's worth doing this sort of thing at this low level, because it's fast. With the multiple laning, as I've said, we've also got the graceful degradation on lane failure. So if one lane, supposing we've got 4 lanes that are working together, if one of those lanes fails, then we automatically start sending the information over those remaining 3 lanes. You've got a reduction in bandwidth, but you're still using the overall link. Other mechanisms which have multiple lanes, they do the laning in a different way, and you can't do that sort of thing with those. You have to basically resend, reconfigure. We don't have to wait for that. Of course, if you've got a redundant link, then you've now detected that this lane has failed, so you can bring up that redundant link, and then as soon as you bring it up, you can share the information over those 4 lanes. If you want hot redundancy, you just have the 5 lanes running all the time, and if one fails, then you've still got enough bandwidth to cope with the throughput. We've got babbling idiot protection, as I've discussed, and we've also got the error reporting, which can be done by broadcast codes. So this is a way of, if there's a possible way of getting the error through to the network manager, the best way is to broadcast it over the network, and it will get there. Okay, so where are we with this? That's the standard. So we're currently working on this interface design, so the University of Dundee and Star Dundee. We're being funded by the European Space Agency, the European Commission, which is European government, and also Star Dundee as well. The design of the SpaceFibre chips, or the IP cores, is going in tandem with the SpaceFibre standard specifications. So we basically do the spec, design the next version of the IP, test it in FPGAs, figure out what was wrong, and then we go around that loop. And we've been around that loop many times already, okay, improving, honing the ideas as we've gone along. Okay, so where we are now, we've got a SpaceFibre VHISSI IP Core. It's compliant to the current version of the standard, which is actually draft F3. It provides the virtual channel interfaces, multiple virtual channel interfaces, broadcast channel interface, management interface. We've got the full quality of service integrated in there with scheduling with 64 time slots. We've got the retry, the rapid retry, maximum of 5 microseconds. We're currently supporting a single lane, but multi-lane support will be, that's our priority for next year. So this IP core is actually available from Star Dundee. We're also working on a radiation-tolerant chip for SpaceFibre, which is called VHISSI, which is Very High-Speed Serial Interface Chip. This will be a radiation-tolerant SpaceFibre interface device using the IP core we're developing. It's part of a European Framework 7 research project with a team of partners from across Europe and Israel. So this device is a fully integrated SpaceFibre interface. It has running at 2.5 gigabits per second. It includes the quality of service FDIR capabilities. It has 2 serializer deserializers, 1 nominal, 1 redundant. And into the device, we've incorporated versatile I/O capabilities. So we've got a SpaceWire to SpaceFibre bridge mode, and then various parallel I/O modes, so including FIFO interfacing, memory interfacing, DMA, and transaction mode, which is designed to simplify software interfacing. So this chip is being designed for simple interconnection to an FPGA, and it's small size, so it won't take up much board area. It's radiation tolerant, and we're currently desperately trying to get all the design finished so we can go to tape out in April. So we expect to have samples in the middle of the year. We've already done a test chip, which I've got a photo of later, and we've just had the radiation test results back from the basic technology on there, and that's looking fairly good. So that's where we are. So this shows the architecture for this device. So here we have the SpaceFibre interface, which is the complete SpaceFibre codec with several virtual channels. And then we have the SpaceFibre bridge mode. This basically provides a number of SpaceWire interfaces. Then we've got the FIFO and DMT mode, which provides a number of parallel interfaces. There's a mode switch matrix, which switches between these 2 operating modes. And there's an I/O switch matrix, which switches between LVDS for the SpaceWire, and LVTTL if you want to increase the number of SpaceWire interfaces, or if you want to use the FIFO and DNT mode. And then there's the nominal and redundant SERDES for doing the high-speed serial data. Okay, so what about the applications of this chip? So the first sort of application is basically using this as a bridge. So you may have a number of SpaceWire instruments that you want to connect to some other SpaceWire equipment, but there's a long distance between them, so you can just put them through one of these bridges, run it over SpaceFibre, and you've got a very lightweight cable. SpaceFibre cable is around about half the mass of SpaceWire cable. If you go to the fiber optics, it's even lighter as well. SpaceFibre electrical running at 2.5 will run over something like 6 or 7 meters. If you run fiber, then we can run easily over 100 meters. Okay, so that's the SpaceWire to SpaceFibre bridge. Supposing you wanted to develop an instrument like a camera, a very high data rate camera, multispectral camera. Very typically, you'll have your instrument, at front-end electronics. You'll connect this up to an FPGA, and then what you want to do is squirt this out at high speed. So what you can do is use the VHISSI chip, you use the FIFO type interface or memory interface, and your data output streams into the VHISSI chip and then out over SpaceFibre using one of the virtual channels. But the other thing you want to do is you want to control your instrument. So what we provide with VHISSI in the FIFO mode and those other parallel modes, we keep one SpaceWire interface available, which we can then connect up from VHISSI to the FPGA, and we can use this for doing SpaceWire-based control and housekeeping. So we can control the instrument over another SpaceFibre virtual channel. We can read back housekeeping information and so on. Okay, so that's the instrument. So you basically, your front-end electronics, your FPGA, you hook it up to one of these VHISSI chips, and that's given you all your communications capability you need. The same sort of thing applies for the mass memory. So at the other end in the mass memory, we can use the VHISSI chip as an interface into the mass memory. Okay, so if we look at complete spacecraft application, then you may have some high data rate instruments, a very high data rate instrument at the top that needs 2 of these 2.5 gigabit per second interfaces. We've got a moderate data rate one which needs 1 of them, and then we've got, down the bottom, we've got a number of let's say legacy or existing SpaceWire instruments we want to reuse. We just put them into a SpaceWire to SpaceFibre bridge using the VHISSI device, and then connect that into the mass memory as well. Okay, if we want to then extend this so we can include control and housekeeping, we then need another component, which is a SpaceWire router device. And then with that capability, we can then add in the control processor. The control processor can use virtual channels to talk to or control any of the instruments, or the mass memory, etc. We can send data from any of the instruments into the mass memory. The mass memory can send information to the downlink telemetry. We can read housekeeping information from all of these pieces of equipment over that one network. If you want to send time information, you can just broadcast the time over the network. If an instrument has an error, it can just broadcast an error code, and the control computer or some other network manager will be able to detect and handle that. Okay, so we have this technology running in our lab, and one of the first things we needed was some test equipment to check out what we were doing and see if it made sense. So we developed this, this is actually one of our small blue boxes. It has 2 SpaceFibre interfaces at the front and also 2 SpaceWire interfaces. And around the back there's a USB interface as well. This shows the block diagram. So we've got 2 SpaceFibre interfaces, SpaceFibre codecs in there, each with 8 virtual channels and a broadcast channel. We've included a SpaceWire router, which is connected to the 2 SpaceWire interfaces and to the USB interface, so we can hook it up to a host computer using USB. And that router is also connected to to 2 virtual channels on each of the SpaceFibre interfaces. So we can route information from SpaceWire over the SpaceFibre virtual channel, or up to USB, or between one SpaceFibre port and another SpaceFibre port, and so on. Because we wanted to test this at full speed, we included, on the other virtual channels, we included some pattern generators and checkers, so we can run each of those at full speed, so the full 2.5 gigabits per second, over multiple lanes, over multiple virtual channels, so we can actually test out the quality of service and the precedence handling. And finally, because we wanted to see what we're actually sending and receiving over the link, we included some analyzers here so we can actually see the traffic. So each interface has an analyzer that can record data. So you're actually able to use this equipment either as an interface or as an analyzer itself by feeding a SpaceFibre link through one port and out the other port. Okay, so this actually shows the analyzer output, and what we've got is the information flowing in one direction here, so time goes down the way, the information flowing in the other direction here, and then, so this is an init3 code, and it's made up of a comma, and then some other symbols which basically form this init3. This is actually showing the initialization sequence. So we were using this just to check the initialization sequence. The analyzer can be triggered on certain events, stores a whole load of data, and then displays it like this. To show the multiple virtual channels, we have what we call the frame view. So here we've got a number of virtual channels. Actually, this is the broadcast channel. Then there's a number of virtual channels here. And then each of these is the frame that's being sent over the link. And again, we've got what's happening in one direction, one side, and what's happening in the other direction over the other side. Okay, so we've seen the Starfire unit, as we call it. In partnership with Axon, we've developed a flight cable for this, which their cable will actually run at 10 gigahertz in a flight configured form, and the connectors they've got, they're slightly bigger than SpaceWire connectors, but they're working on a reduced-sized version of this. This chip here is the Radix 5 test chip that's basically testing the SerDes and the other logic. The other logic's been through the radiation testing. And the other picture you can see is in our lab back in Dundee, where we've got, we're actually testing one of our early implementations of SpaceFibre against 2 independent Japanese implementations, and we were doing interoperability testing. And after a bit of finger trouble and getting things working, this was the result. Okay, and this is some tests we did at ESTEC. So this is ESA's Research and Technology Centre in Holland. And you can see here there's a couple of our Starfire units, and these are actually connected onto this board, which is containing some fibre optic transceivers. And then this purple bundle here is basically 100 meters of fibre optic cable. And that fibre optic cable has been designed for flight applications. So it's using a core that doesn't degrade significantly under radiation, and the sheath has been made sort of to withstand wide temperature range and all that sort of thing. Okay, so we're well on the way with this. The current plan is that next year, it's not very long now. Next year, we're actually starting on the formal standard specification. So we have a draft standard specification, and then next year it goes to the ECSS. Once it does that, it will take about a year before it becomes a published ECSS standard. In the meantime, we have a number of beta activities that are going on in Europe. So the first is next generation mass memory. This has been, so we're using SpaceFibre as the, if you like, the interface and the interconnection mechanism between memory units. So we're actually, the University of Dundee and Star Dundee are working with Astrium and IDA in Germany on this particular project. So we're also working on a high processing power DSP with Astrium in the UK. And again, Stardundy in this case is actually providing the hardware, which has, it actually has a reasonably radiation hard or radiation tolerant. I think it's about 30k rads or something, DSP processor, commercial DSP processor. And we're providing an FPGA, Xilinx-based FPGA with SpaceFibre interfaces, and they operate in a dual redundant configuration for recovering from faults and single event upsets and so on. There's another project which is high-performance COC-based computer. There's also an FPGA-based generic module and dynamic reconfigurator, and a Leon processor with fast Fourier transform coprocessor, which is, I think, is being developed for SAR type, onboard SAR processing type applications. Okay, so there's from our perspective, these are all providing feedback on our IP core. They're all using our IP core, and they're providing feedback on the IP core and on the standard specification, and should there be any modifications that we need to make. We're also working on a SpaceFibre flight engineering model implementation, which is basically aimed at raising the TRL of SpaceFibre. So this will use components that have all flown before, so it will just raise its TRL enormously. We'll be using a microsemi AX2000 device, which will hold basically the SpaceFibre digital logic, and we're using the TLK2711 as the SerDes. And so anyway, we're working with Astrium in Germany on that board design. Okay, so in conclusion, SpaceFibre has been designed specifically for spaceflight applications. It runs at multi-gigabits per second. It provides galvanic isolation. It has integrated quality of service and FDIR capabilities. We've provided compatibility with SpaceWire at the packet level. The design is very efficient, and we now have several application demonstrators being developed. We've already shown in an earlier revision successful interoperability testing. I guess this was successful in that, yes, we got it to work, but also it was successful in it showed up some problems that we had and issues we had both with the standard and the various IP core implementations. So that was very beneficial. The formal ECSS standardization is scheduled for 2014. So I expect that the final standard will be published in middle of 2015. In the meantime, we're already working on the radiation-tolerant chips, and we have test equipment and IP cores available now. Okay, so thanks to various people for funding this work. Okay, and if you have any questions, I'll be happy to answer them.
With respect to broadcast messages, is it possible to assign different priorities to different kind of messages? For instance, if you want to distribute timecode messages, I think they should have quite a high priority in order to reduce variability.
Yeah. Yeah.
And for events, you don't need such high priority.
Yeah. So broadcast messages have highest priority. So they go. If you're in the middle of sending a frame of data, the broadcast message will be interleaved inside the, in the middle of that frame. So broadcast messages get broadcast immediately.
So even if you have an event which is going to be broadcast, it will interrupt the transmission.
Yeah, so it just gets as soon as it's ready, it just goes. So let me just finish your question. So the issue arises if we're in the middle of sending a broadcast code and then an error occurs on the link. Okay, so then we take this 5 microseconds to recover from that. So now it means we've immediately introduced 5 microseconds of jitter in our time distribution, which is really bad. So what we have is if ever a broadcast code gets resent, there's a bit in that broadcast code which we call the late flag, which gets sent. Okay, so a broadcast code that gets resent is marked as being late. Now, if that's sending time information, the receiving application can then decide not to use that time code to update its local counters. If it's an error event, then even if it's late, you want to know that that error occurred.
And again, with broadcast messages, how do they correlate to the time slots? So do you reserve a certain amount of time within each slot for broadcast information, or would that completely block one of these time slots?
Yeah, so what we've done is because we could have broadcasting that starts babbling, so we actually allocate a certain percentage for broadcast messages. So there's an overall, there's effectively a bandwidth counter, so a bandwidth credit counter for broadcast messages, which basically counts how many broadcast messages are going over the link, and then to stop too many being broadcast. So we allocate a certain percentage because we expect them to be relatively low percentage of link utilization. So that's to stop babbling broadcasters. And your question was?
My question was if we have this allocation of time slots to certain virtual channels, what happens if within one of these time slots we have broadcast message? Would that completely block this?
The broadcast messages are quite short, so they won't have a significant effect on the time. And there's always effectively if you're sending information in a time slot, you just need to make sure that you're only using sort of like 98% of the link bandwidth, not 100% of the link bandwidth.
Thank you.
The other thing there is we can use broadcast codes to do time slot synchronization. So you can either do that directly, so you can have time codes that come in and say synchronize, 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 or you can do it by sending out a time code which has the time in it, unsegmented time code, which fits inside a broadcast message. So you can say this is the time, and then you can use a local time counter for doing your time slot synchronization, which is the preferred method. But you can use both.
Yeah, back to broadcast messages. I noticed on one of your very early charts that the diagram showed that it was bidirectional. Is that actually the way it is for broadcast messages?
Yes, you can send and receive broadcast messages. So the broadcast messages are effectively broadcast in a similar way to the way SpaceWire broadcasts time codes. So if you're familiar with that, basically there's effectively a counter at the inside the broadcast header, which basically prevents a broadcast message going out to a router and then being sent back down the link that it was sent on. Okay, so we prevent circular propagation. The broadcasting information is very easy in some network topologies. So if you've got something like USB, it's easy because it's a tree structure. Okay, but then because you've got a tree structure, it's very difficult to introduce redundancy and have cross-strapping. SpaceWire and SpaceFibre are designed to support cross-strapping and have arbitrary architectures. So we needed to develop a mechanism where we could do broadcasting even though we had that arbitrary architecture topology. And the broadcast codes basically cover that. There's two mechanisms we've got, and we can actually use either of the mechanisms, but the one is basically to use a counter, and it prevents circular propagation of the broadcast messages.
The message priority. There were some studies back when Token Ring had message priority that the message priorities could actually propagate back up into the tasks, and you could get priority inversion both at the message level and a propagation of the priority inversion from the limited number of priorities on the message bus all the way back into the thread scheduling. Has anybody actually looked at that, say from, I guess, University of York or University of Birmingham? Because those guys, those are the ones who seem to have the scheduling knowledge near you.
Right, okay. So Yeah, we hear many different stories about priority and this sort of thing. So it's a bit like FDIR as well. There's different schools of thoughts, and some people want priority, some people want scheduling for determinism, and some people want bandwidth reservation, which is basically why we've done all three. It's one of those reasons we've done all three. It depends on what you actually want to do with the priority mechanism. Very often, it's about providing determinism, which can sometimes be about actually providing bandwidth reservation. So I think people need to think carefully about what they actually want and then use the most appropriate mechanism. And very often, I think it's actually bandwidth reservation that's required. So with a SpaceFibre network, there's one way you can view the multiple virtual channels is like each virtual channel, once you've got the routers in there, provides a completely separate space, the equivalent to a SpaceWire network. So if you've got 8 virtual channels, for example, it's like having 8 totally separate SpaceWire virtual channels, and these don't interfere with each other.
I was going to say, it's funny how bandwidth reservation, I guess 30 years ago, used to be called fair share scheduling, but it's just been renamed.
No, yes, okay. No, I think it's one of those things. It's like we try not to develop anything new. We just try to make old things work better.
Very good. Okay.